Waiting for my computer to wake up this morning. I don't have anything really new except for that I had given you the wrong number on the homework assignment. It was homework 18, not 17. That covers the calorimetry. And it's in a folder for chapter 5, so look for it there. I've gotten most of the vocab 5s in, but not everybody. So if you haven't done vocab 5, make sure that you are working on that. And then we do have a quiz this Wednesday. And additionally, an exam a week from today. So the quiz is going to cover the calorimetry stuff we've been talking about. Talk a little bit about conservation of energy, the first law of thermodynamics. And we'll talk a little bit today about heat of formation. I don't know how much of that will show up on the quiz because I want to make sure that we also get the chapter 9 content on diffusion and effusion and those graphs of temperature and speed. So that's kind of what's on the radar. So the exam will cover chapter 9 and chapter 5, gases and heat. Now this week and next week in lab, if you have lab, you are going to be doing calorimetry experiments using the coffee cup calorimeters that I was showing to you. You should be good to go for this week's experiment. I'm going to talk today a little bit about some of the experiments that you might, the experiment you're going to do next week. I know that different professors kind of do the math a little bit differently. So you can do it the way that you're comfortable with, but remember that on your test, ultimately, I'm going to care about what the sign is. So I know Dr. Hughes was saying, oh, don't worry about the sign. So if you have Dr. Hughes, she may kind of blow that off, but I'm going to care about what the sign is. So do be paying attention to those things. So what we had talked about on Friday was we were talking a little bit about how if we are working with no work, not working, in chemistry, then we're mostly just talking about heat changes. And so we had this idea that the internal energy which could be either E or U, and I think your book uses U, but a lot of my images have an E in it. That's all of the individual kinetic and potential energies of all of the particles and pieces of what's going on. But the change in internal energy is equal to Q plus W, so the heat plus the work. But for chemistry, the only work that we really have is pressure volume work, the work of gases either expanding or compressing. And so usually we assume that work is equal to 0. We also have been working with the equation that Q, which is the only thing we've really been calculating, is MC delta T, or sometimes you'll see MCS, so the subscript meaning specific heat capacity. And then, so we've plugged in several times the mass of, say, water, the heat capacity of water, the change in temperature of the water, or the mass of a piece of metal, the change in temperature and the energy in order to find what the specific heat capacity was. We've done it in a couple of different ways. And what we've discovered with calorimetry is not only can we do this for one thing, since we have conservation of energy, the whole universe has the same amount of energy, then any energy that we calculate for one part of the universe is going to be the opposite in sign for the rest of the universe. So Q of the surroundings is equal to the opposite of Q of the system. So we did an example on Friday where our system was a piece of metal. You can't stick the thermometer in the piece of metal very easily. So we calculated Q for the water that we put the metal in, and then said, okay, we changed the sign from positive to negative for the system, and then found the Q for the system that way. So we can use this idea, and we're going to continue with that a little bit. So this becomes even more helpful when our system is a chemical reaction, because the chemicals are sort of embedded in the surroundings, in the water. Why this is stuck? Okay. All right. So one of the things that you're going to do next week, in addition to looking at a chemical reaction, you're also going to look at the heat capacity of the calorimeter. So we have said, oh, we're basically going to assume the water in the calorimeter does all of the absorbing. But in reality, the styrofoam cup, the lid, the air, the thermometer, they're also going to absorb things. So Q of the surroundings is equal to Q of the water plus Q of the calorimeter. Or I'll sometimes just substitute Q cal, okay? So this week, the temperature change that you're going to have is really small. And so saying that this is next to nothing is really a valid thing. It's really not affecting what we're doing. But next week, we have a big temperature change. And that big temperature change is going to mean that, yeah, we really have to include that. So what I'm going to look at first is, how do we include Q of the calorimeter? Because this is a substance. And for a substance, we can use CS, the specific heat capacity. This has many parts. Calorimeter does. And so the thermometer absorbs heat a little bit differently than the cups do, and that absorbs differently than the air does. And so we can't really say per gram, because are we talking about one of the grams that belongs to the cup or one of the grams that belongs to the thermometer? So per gram, as we do a specific heat capacity, doesn't make sense. So for this, instead of specific heat capacity, we just use heat capacity. Is that heat capacity is measured in joules per degree Celsius. Specific heat capacity is measured in joules per gram degree Celsius, okay? So this, we're looking at individual grams, and then that way we can scale it to however much water we have. Whether we have a few drops of water or we have an ocean of water, we can adjust this. This one doesn't have per gram, which means I have to be talking about my specific calorimeter. Your calorimeter might absorb slightly differently than mine does. So you each have to calculate it on your own in lab. Something else I want to point out about units is that I will consistently do degrees Celsius, because in this chapter, it really is better just to stick with degrees Celsius. But the units you will sometimes see include Kelvin. These are identical, because the size of a degree Kelvin is the same as the size of a degree Celsius. If my temperature rises from 0 degrees Celsius to 10 degrees Celsius, that's the same change as going from 273 to 283. It's still 10, whether I do it in Celsius or Kelvin. What tends to happen is if people try to switch it to Kelvin, they end up either adding the 273 to one number and not the other, or just adding it at the end, and then they get this huge temperature change, which isn't really big. So people make mistakes. If you can do it, fine. It doesn't really do anything more than have you do a little more calculations. So I just recommend you stick with degrees Celsius, and I'm just going to do that for this chapter. I don't think anybody in our department is going to say, no, you have to change it to Kelvin. Okay. Okay. So I want to do an example problem, and I finally got this computer working here. So let me pull it up. The Q of the calorimeter is going to be the Q, or is going to be the difference between the ideal scenario. So we said in an ideal world, we can ignore the calorimeter. This would be 0. And so all of the surroundings would be this. So what we're going to do is we're going to find Q of the surroundings and find out what's the difference between that and actually having just the water. And the difference between those two is going to be the calorimeter Q. I want to show you how that will work. All right, so this is our sample problem. We're going to mix 100 grams of water that is at 75 degrees Celsius with 100 grams of water that's at 25 degrees Celsius. And so just intuitively, if I mix these two things, they're equal in amount, they're both water, what would I expect the temperature that they meet at? What would I expect thermal equilibrium to be? What do you think? You look like you have a thought, Sydney, no? If both of these are the same amount, both of them are water, right? So they have the same heat capacity, where would I expect them to meet? So Charlie, you have a suggestion? 50, so halfway in the middle, right? Does that seem like that makes sense? Okay, so we expect it to be 50 degrees Celsius, and that works out mathematically. Finding the final temperature using our Q equations is kind of the hardest way to address these, so I'm going to simplify this. So we are going to look at Q for the hot water and negative Q for the cold water. So in an ideal world, those would be the only things that matter, and we wouldn't care about the coffee cup. So this is plugging in all of the numbers. On the left-hand side, we have, there we go. On the left-hand side, we have 100 grams of water, the heat capacity of water, and then T final minus 25. On the right-hand side, because Q hot and Q cold are opposite in sign, I've got a little negative sign in front of there. And then I have 100 grams, because it's also 100 grams, the same heat capacity, and then TF minus 75, okay? So this is how we would set it up. Now, normally in lab, you're not going to hit exactly the same amount for both things. So you would actually have to go through and calculate, these things in order to figure out final temperature. But, oops, my lines didn't show up. We have 100 degrees on both sides. Those cancel. We have the 4.184 on both sides. So those cancel. So we just end up with TF minus 25 is equal to negative TF minus 75. So what I'm going to do is I'm going to take this negative and I'm going to distribute it through the parentheses. So I'm going to have the negative TF, but then I'm going to have the negative of the negative. So this will be positive. And that's a tricky part for a lot of people who don't do a lot of algebra. But that's the way that works out. So now I want to get all of the TFs on the same side. So I'm going to add a TF here, which means I need to add a TF here. So I'll end up with 2 TFs. And I'm going to add 25 to both sides because I've got the negative 25 here. So I'll add 25 here, and I'll add 25 here. So when I simplify this to have the TF on the same side and the numbers on the other, I end up with 2 TF is 100 or TF is equal to 50. Okay, so your gut is right. It does work out that way mathematically. Okay, so for the sake of identifying the system and the surroundings, we're going to say that the cold water was in the calorimeter, okay? So the calorimeter is starting at the same temperature as the cold water. It's starting at 25 degrees Celsius. When the water warms up, so does the calorimeter. It's reaching thermal equilibrium, not just with the hot water, but also with the styrofoam cup and the thermometer and those things around it, which means that those things are also absorbing the heat. So what ends up happening, oh, there's my crossouts. Those were supposed to appear earlier. What ends up happening is that instead of getting 50 degrees, usually it's a little bit lower because some of that heat has actually gone into warming up the calorimeter and not the water itself. Okay, so this is what you're going to do in lab next week. Is you're going to see, okay, how much heat is being absorbed by the calorimeter. So we are going to first calculate how much was given off by the hot water, the change from the 75 to the 48. That's all of the heat from the system. And that's all of the heat that was absorbed by the surroundings. And then the part of the surroundings we can measure easily is the cold water. So we'll figure out what that is. Any difference between them is going to be the calorimeter. So let's see how that works. So I say in quote lost because conservation of energy says we don't actually lose energy. It can't be created or destroyed. It's just going somewhere inconvenient. Instead of going into the cold water, it's going into the calorimeter. All right, so hot first, we're taking the 100 grams, the 4.184, and then this time, instead of plugging in 50, the ideal, we're plugging in the real temperature. So we have 48 degrees because that's where it really reached equilibrium. Okay, so we're going to find out how much energy was given off by this hot water. So we plug all of this in, and I encourage you to do that at some point. You're going to find that this works out to about negative 11,300 joules. Now, why is it negative? Yeah, since my final temperature is smaller than my initial temperature or my starting temperature, that gives me a negative sign there. And what does the negative sign tell me about the process? Is it endothermic or exothermic? This is one that will be on your quiz. You have to identify when things are endothermic and when they're exothermic. So one of the things I'll give you is Q is negative. That's going to be what? Endothermic. It's actually exothermic because it's leaving the system. So our hot water is the system, but thank you for actually responding. I appreciate that. So it's leaving the system and its own energy is going down. That's why it's negative. Okay, so since it's leaving the system, it's negative. All right. So then we're going to plug in for the cold water. So we had 100 grams. We had 4.184, same heat capacity, same final temperature. Remember I said that on Friday. Your final temperature should be the same between both things because this only works when we're at thermal equilibrium. And this time, is this going to be positive or negative? Positive because the 48 is greater. Okay, and the cold water had to absorb energy in order to warm up. So we plug in all of those numbers and we get 9,600 joules. Okay, so we don't have the same amount of heat that is being given off as we have absorbed. Now, this doesn't actually violate the law of conservation of energy. We just need to know where that energy went. So instead of going into the cold water, where did it go? Yeah, up here. It went into the calorimeter, that calorimeter that also warmed up. The styrofoam cup, the air, the lid, the thermometer, all of those things also warmed up. Okay, so we said that the Q of the surroundings is the opposite of the Q of the system. So the Q of the system was the negative 11,300. So the opposite is that is the Q of the surroundings. And the Q of the surroundings was made up of the Q of the water and the Q of the calorimeter. So this is kind of the key thing to figuring out what the heat capacity of the calorimeter is. So if we use both of those negatives to make a positive 11,300 for our surroundings, and then we subtract off the 9,600 to find the difference, we end up with Q of the calorimeter is 1,700 joules. And that seems like a lot. 1,000 joules, 2,000 joules, that seems like a lot. But compared to all of the temperature change, that's only, what, about 10%, maybe less? Now, what we also have to look at is that this is in this particular circumstance, when the temperature changed that much. It's not going to absorb that much heat if the temperature only changes by 10 degrees, and it will absorb a lot more if it changes by 100 degrees. So we need to figure out how much it is per degree Celsius. So anybody still need this slide? Okay. So just following up that we're looking at the calorimeter is the difference between the ideal and real. So really it is absorbing 1,700 joules. But that amount depends on the temperature change. So the heat capacity then is what we just calculated, the heat divided by the change in temperature. And this is where we have to remember, what was the calorimeter part of? Was it part of the cold water or the hot water? So we said it was holding the cold water. It started out as the same temperature as cold water. So its change in temperature was also 25 to 48 degrees. And so overall, the change was 73 joules per degree Celsius. And then if I keep using the same calorimeter, anytime I use that calorimeter for another experiment, then I can say, oh, let me adjust my experiment by this amount. So I know for me, this was kind of one of the hardest parts of calorimetry to wrap my brain around, because part of it uses the grams and part of it doesn't use the grams. When I ask you questions in class, generally I'm just going to ignore the calorimeter, but I know that you have that lab next week where you're going to include it. So this is how you do that calculation for lab next week. And if you take more chemistry classes, particularly if you're doing physical chemistry, or if you go into physics, like all of these little details matter when we get to more precision, more significant figures. And so it's good to have the heads up that we can't ignore things all the time. All right, anybody need this slide? So I said we were going to be working on calorimetry with chemistry. And this is where we get into enthalpy. So what is enthalpy? Your book doesn't give a great definition of this. So it's kind of the internal energy, but it also includes pressure volume energy, only in an opposite way from internal energy. So it sort of cancels out. The book goes through the math derivation. I'm not going to go through that. What we basically just assume is this is heat. So we talk about the heat of reaction, the heat of fusion, the heat of solution. That all refers to enthalpy. So there are subtle differences. We're not going to worry about the subtle differences. I'll let Dr. Hamilton explain the subtle differences in pChem. So the change in enthalpy, remember change was what heat was. The change is going to depend only on the initial and final conditions. So your book talks about the difference between a state function and a non-state function. A state function, all we care about is the beginning and the end. Okay? And so this one doesn't matter what path we took to get from the beginning to the end. So for example, the distance between here and Louisville is the same distance whether I hop on 64 and go over, or if I go down to Bluegrass Parkway, or if I go up to 71 and then take 71 over. All of those have different distances. Those are path dependent. But the difference between where we are and Louisville as the crow flies, that doesn't matter on how we got there. Okay. In chemistry, we use capital letters like this H, so it's a capital letter, to indicate that final and initial are the only thing that matters. So that's why in our delta T, we use a capital T for the temperature, because it doesn't matter how we got from 25 degrees Celsius to 48 degrees Celsius. It's only the final and the initial that matter. Q and W, work and heat, do depend on how the system changes. Because usually as one of them changes more, the other changes less. There's sort of a give and take there. So we call these non-state functions, and we use lowercase letters. So I could see on the test, probably not on the quiz, but I could see on the test asking a question, which of the following is a state function, and giving you 3 choices that have lowercase letters and one that has a capital H or one that has a capital T. And so looking at the capital versus the lower is what would indicate to you, is this a state function or not state function? All right, does anybody still need this slide? Okay, so the change in enthalpy is related to Q because we assume chemistry is happening at constant pressure. Okay, if it's constant pressure, there's no work, and so we can ignore that pressure volume stuff. We just say, okay, it's just heat. But delta H is per mole. So just like the specific heat capacity is per gram, so we can scale it, delta H is per mole, so we can scale it for more moles or fewer moles. The little subscript P on the Q means that we're at constant pressure. For our class, we assume we're always at constant pressure, so we're not going to worry about does constant pressure apply or not. But again, if you take pChem, that won't always be the case. And we already know how to find Q with calorimetry, but since we're talking about chemical reactions, we do need the surroundings that we can measure. And so we will kind of stick in the realm of aqueous chemistry, things in solution, because we know how to measure water very easily. And we could do this with other situations that are harder to measure, but for this class, we're just sticking with situations that happen in water. All right, am I good? All right, so reactions and solution, and specifically aqueous solutions. The system is going to be the chemicals that are in the equation. So if we have NaCl aqueous, the sodium ions, the chloride ions, those are the system. The water surrounding it is going to be the bulk water. That is going to be our surroundings. Okay, so they're all mixed together in the same calorimeter, but we're measuring the water, not the individual molecules as part of the chemical reaction. So I'm going to look at a very specific reaction here. Anybody know what that first chemical is? Yeah, that's hydrogen peroxide. So we talked about this a couple of times. It decomposes to form oxygen and water. So that's what happened when I poured the peroxide into the pumpkin. The enzyme helped to break it up. So this is kind of a slow process. We're going to assume there's a catalyst in there, not really say much about the catalyst, but we're going to assume there's a catalyst. Okay, we'll see in a little bit that the balanced equation is going to make a difference. All right, so let's look at our example here. We have 101 milliliters that happens to also be 101 grams of 0.882 molar H2O2. So I calculated that was roughly the concentration of 3% peroxide, which is what you have from a grocery store. So when 101 milliliters, also 101 grams of 0.882 molar H2O2 is decomposed, which is this chemical formula, using a catalyst, so it's there, in a calorimeter, the temperature of the solution rises from 19.2 degrees Celsius to 43.6 degrees Celsius. And we want to know what is the enthalpy of the reaction. Okay, so we've got all the parts we need here except for the specific heat capacity. So you would always have to be provided the specific heat capacity, but you're probably going to recognize that it's the same one we keep using for water because this is aqueous solution. All right, so what is the surroundings in this situation? Water, right? So as I mentioned last week, water is almost always going to be our surroundings. So the system is what's written in that chemical equation there. Now, some people will notice, but there's water in the chemical equation. This amount of water that is produced is going to amount in this entire calorimeter to like 2 drops of water. So this water that's produced here is sort of irrelevant. We're going to ignore that water. The bulk water, the water that's not part of the chemical reaction, that's the surroundings. All right, so to find the enthalpy of the reaction, we have to look at the surroundings first and then relate that to the system. Okay, so delta H, remember, the enthalpy of the reaction is the Q of the reaction. And that is going to be the negative of the Q of the water because the water is the surroundings. Anybody still need more time? Okay. All right, so cue the water. And hopefully you are getting good at plugging these things in. If you haven't looked at homework 18, you're going to have the opportunity to do that a little bit. But this is why I say try and plug these things in. Might be a good idea as you go through your notes later today to stop at the point where it says cue the water, cover up this, and see if you can come up with this part yourself. Can I come up with 100 times 4.184 times 43.6 minus 19.2? All right, so we're ignoring the chemicals in our mass here. So that mass includes water, but it also includes peroxide and oxygen and things. We're going to ignore that because, again, it's just teeny tiny. And we're, in this class, always going to ignore the calorific. So when I plug all of these things, I get 100 or 10,300 joules. Should it be positive? Yeah, because we have a higher temperature at the end than the beginning, and because the water is absorbing heat. So that's endothermic for the surroundings, which means the system is exothermic. So what should I do next? I have Q for the surroundings. How am I going to find the enthalpy of the reaction? What does this tell me about the reaction? It's the inverse, the opposite sign, right? So Q of the reaction is going to be just slap a negative on that. Oops. Now, is this the same thing as delta H? Look back in your notes when we talked about Q and delta H. Are they identical? Seeing a couple of nods. They're very, very similar, but we need to account for how many moles there are. Okay, so I get this much when I use 101 grams, but if I did this with 201 grams, I would have nearly twice as much energy, right? So to get delta H, I have to divide by the number of moles. So how do I find the number of moles? We can do the stoichiometry there, but the first step that we actually want is finding moles in stoichiometry, right? And so if I have a solution, then I have a molarity. How do I find moles from molarity? Not from molarity. Molarity is moles per liter. So what do I need? This is a tricky one. This is why I spent so much time in that chapter talking about the difference between a solid and a solution. What are you going to do, Charlie?
Grams to milliliters and milliliters to liters.
Right. So this is why I told you at the beginning that it was 101 grams, also 101 milliliters. I told you that it was the same amount. So if you didn't have that, technically you'd need the density, but they're the same amount. And then since we need liters, we're going to go 101 milliliters to 0.101 liters. So for a solution, we don't need the periodic table at all. We just needed to know the concentration, which was given to us in the problem, and the volume, which we converted to liters. And that's how many moles of the peroxide we have. Okay, so what am I going to do with those numbers? I've got Q of the reaction and I've got moles. I've got 4 possible arithmetic operations. So add, subtract, multiply, or divide. Divide. So delta H is Q divided by moles. So this was Q of our reaction. Plug it in there. Moles is right here. Plug it in there. And then we ended up with, oh, and I dropped my negative. The delta H of the reaction should be negative 116,000 joules per mole, or we can just put it in kilojoules. And what does that negative tell us about this process? That this is an exothermic process. So if delta H is negative, we have an exothermic reaction. All right, are we good on this slide? Okay. So I had you look at the section on enthalpy of formation. So it's just a few paragraphs. But we use this to help us with reactions that maybe we don't want to actually physically do the reaction. Maybe it's difficult to do. Maybe it's dangerous. So we can use tables of enthalpy of formation. Remember that delta H doesn't care how we got from the reactants to the products. It only cares what the initial and the final conditions are. So if we can know something about peroxide and something about oxygen and something about water, we can pretend like instead of going directly there, we took a different pathway and still find the difference between them. So Appendix G in your book has thermodynamic tables, and it's going to list delta H. It's also going to list 2 other state functions, delta G and delta S. We won't get into those too much. We won't get into those at all this semester. We'll get into them a little bit next semester. So this is where we would look for this information. And what's listed there is the enthalpy or free energy or entropy for the other 2 of formation. So that little F there means formation. So then what we would do is use those terms and find what are the products, what are the reactants, and subtract the reactants from the products, final minus initial. So I would just add up my products were water and oxygen. And my reactant was the H2O2. And so I would take water and oxygen minus H2O2, just the numbers from those tables. That's final minus initial, and that should give me my heat of reaction. So when I look these numbers up in the tables, and your book actually didn't have H2O2 aqueous, it had liquid or it had gas, so I just picked something. I might have looked it up. I can't remember which one I picked. So I'm going to take these 2 and subtract off that one, because those were the products and the H2O2 is the initial, the reactant. It looks like this. There are a lot of parentheses in there to keep track of things. And this is where our balanced equation comes in. Because remember, it was 2 waters, 1 oxygen, and 2 peroxides. If you look back in your note at the balanced equation that I gave you when we started all of this, that's where this 2, and this 1 come from. But really, I want to know what's going on for just 1 mole of this, not for 2 moles, because remember we said delta H per mole. And so that's why we divide by 2. if we plug all of that in, we end up with negative 98 kilojoules per mole. And so our experimental was negative 116 kilojoules per mole. So I was a little bit off in my experiment. That happens, but we're still right around 100 kilojoules per mole negative, which is exothermic. Okay, are we good on this slide? Oh, there was one more thing I had to say. So if we know the delta H of formation for each chemical, if it's listed in those tables, all we do is subtract products minus reactants, which is final minus initial, and we use the coefficients to multiply by those energies. That's what helps to keep it balanced. All right, so I want to look just for a second at what we mean by delta H of formation, what those numbers imply in the tables. So formation is making a substance from its elements. Okay, so making water from hydrogen and oxygen. And for technicality purposes, it has to be oxygen in its normal state. Its standard state is gas. And if there's more than one form, it's most stable form. So oxygen actually has a form that's O3, ozone, but we use the O2 form because that's more stable. So if we think about this, what this means is for an element to be made, to have its formation, it would be making itself from itself. Well, that should be zero energy change. So the delta H of formation of elements is always going to be zero. When we look at these equations, we will notice there's always only one product because I don't want the formation of water and oxygen. I don't want the formation of salt and some other thing. I want the formation of just one thing. Yeah.
So zero is like pure form.
For pure elements. So we saw the oxygen, O2 was zero. So if we balance the equation for water, we have 2's here. And if we were to do a really good experiment, we would come up with this energy change. And this looks like the enthalpy of formation of water because we got element 1, element 2, only one product, but we want to also have only 1 mole. So the number that we find in the table is actually half of that. So we'll talk a little bit more about this on Wednesday, but I usually ask on the test for you to write the equation of the formation of some chemical, like water, something simple, from its elements. And so you just have to put what are those elements, and then an arrow, and then that product, and then balance the equation. All right, questions?